Next up, we have 3 problems in a row that are basically the same equation, just thinking about it a little bit differently for each time. So we're thinking about wavelength nature of light in a double slit experiment. And so we have double slit pattern on the screen. The screen is moved farther away from the slits. What will happen to the fringes? So this is that we have light coming through here, and it's going to go through the 2 rays, and we have that light gets diffracted, and the way that it gets diffracted kind of makes these patterns of bright and dark spots on the wall. And if I move this farther back, then these locations of the bright and the dark spots get farther away, farther apart from each other. All right, it just has some more distance to spread out. This is also easy to see from equations. So the spacing between the bright bands, that delta X spacing right there, is approximately equal to lambda, the wavelength of the light, times the length, that's this distance here, over d, that's that distance there. So wavelength and d haven't changed, but if you move the wall farther back, the screen farther back, that will get bigger, and that will make the spacing between the successive bright bands get farther apart. So it works in equations. It also works if you just think about it. Now we have a laboratory experiment when a red laser pointer is shined. If green light is used, what will happen to the bright fringes? So we'll look at the same equation, lambda L over D. So now we're keeping L and D the same. The geometry is the same, but we are switching from a red laser pointer to a green laser pointer. If you can't remember that red has a longer wavelength, that is something that's on the equation sheet. So the last page on the equation sheet has the wavelength that correspond to different colors of light. So that would be a place to check there. But it seems like most people have just sort of gotten to where they can reason that the red laser pointer has the longer wavelength without having to look that up. But there's no reason to not look it up if it's there. So if we switch to a shorter one, that's going to go down, which means that's going to go down. And the distance between the successive bright spots, that right there will get smaller. So those fringes will get closer together. Next, laboratory experiment. Slits are moved closer together. What happens to the bright fringes? Again, with the equations, this is pretty easy to see. So we have delta X is lambda L over D. Move the slits closer together, that is making D get smaller, which means that delta X has to get bigger. So that has to be the answer to that. You can also, again, kind of reason this out physically. We know that diffraction is most prominent when basically the wavelength is big compared to the obstacle that it's looking at. So as we move to as we make D be smaller, we expect that this is going to be sort of a more wave-like behavior is going to come out of this experiment. So we expect that diffraction should happen more as this slit here gets smaller and smaller. These 2 slits get closer and closer together. Sort of the amount that these things spread out should go up. So either way, the answer to that is C. And then we have one quantitative question, and this should be a fresh question because I just pulled it from your midterm. So we have a double slit experiment, blue laser wavelength of 488 nanometers shined through 2 slits, and a pattern is observed 1.5 meters away. So that's our lambda, that's our L. And the distance between the center bright band and the 3rd order bright band, so that is the m equals 3 band is 12.8 centimeters. So this is, got to do something before we can just answer A, which is that we have to actually figure out a couple of ways to do this. One way is to use the equation that has distance is m times lambda L over x. So we're going to the third order bright band, so that'll be 3 times 488 times 10 to the negative 9th meters times L, which is 1.50 meters, divided by x, which would be 12.8 centimeters, so 0.128 meters. Do that in your calculator. 3 times 488 half, and I get 1.7, and we're going to 3 sig figs, 1.72 times 10 to the negative 5th meters. And that's your answer. You could also do this using the equation that we were doing the last couple of questions, which is that D is lambda L over delta x. But you'd then need to figure out delta x. So now I have the distance between the center and the third order bright band is 12.8 centimeters. So delta x here is going to be 12.8 centimeters divided by 3. And either way, you'll get the same answer. Next is another plug and chug question. So what's the angular separation between the central maximum and the second order maximum? So what we're looking for here is between the center maximum and the second order maximum. We're looking for that angle right there. And there's an equation for that. So it says m sine theta, d sine theta is m lambda. And so solve for sine theta. That'll be m, which is between the central maximum and the second order maximum. So we're looking at m equals 2 times 488, 10 to the negative 9th meters, divided by d, which we now know to be that number right there, 1.72, 10 to the negative 5th meters, and 2. That's 0.0569. And now that's what sine theta is. So in order to get that to an angle, I need to do the inverse sine of that, which gets me to 3.26 degrees.